Welcome to the Deep Dive, presented by Knowledge Flow. Have you ever paused to consider how a camera lens precisely captures a fleeting moment, freezing it in time?
Or maybe how your own eyes effortlessly transform raw light into the vibrant, detailed world you perceive every single second.
It's really far more than just intuition. It's the astonishing science and engineering of light in action.
Indeed. Our mission today, as always, is to cut through the noise, extract the most important insights from, well, a wealth of fascinating material.
And deliver those aha moments that make even the most complex topics truly click for you.
That's the goal.
That's right. Today, we're taking a deep dive into the captivating world of optical engineering. We're going to unravel the fundamental principles that govern how light behaves, explore the ingenious devices we've created to manipulate it.
And even peek behind the curtain of our own incredible visual system. It's quite the journey.
You'll discover everything from the tiniest particles of light to the design of massive telescopes that peer into distant galaxies.
And the very materials that make these optical wonders possible. It's a huge field.
So get ready for a journey filled with surprising facts, practical applications, and hopefully a fresh understanding of how light profoundly shapes your everyday experience.
Absolutely. From the screens you look at constantly to the way you see the stars above.
All right, let's unpack this. We're starting our deep dive by getting to grips with the core principles of optical engineering.
Okay.
This field, at its heart, it's all about using established optics techniques to create innovative designs and instruments. It's where vision quite literally gets built and refined.
And it's far from just theoretical. Leading institutions in this field are really at the forefront, guiding the design and fabrication of incredibly precise optics.
Right.
They operate modern facilities with expert technical staff dedicated to grinding, polishing, measuring, and aligning some of the world's most challenging mirror systems.
Yeah, the precision required must be immense.
Oh, absolutely. Think about the almost unimaginable precision needed for extreme telescopes.
It's truly mind-boggling when you consider the real-world scale of these projects. Imagine students and seasoned professionals working side by side on monumental endeavors like the giant Magellan telescope, which promises to be incredibly powerful.
A huge undertaking.
Then there's the Large Synoptic Survey Telescope, designed to map the entire visible sky every few nights. That's just incredible speed.
Yeah, the data output alone is staggering. And let's not forget OSIRIS-REx, that unmanned space probe launched back in 2016.
The asteroid mission.
That's the one.
Yeah.
Designed to land on an asteroid and return to Earth with a material sample. Optical engineering is absolutely fundamental to the success of all these missions.
No doubt about it.
Absolutely. Moving from that grand cosmic scale to something a bit more intricate and closer to home, let's talk about the light wave concept.
Okay.
This technology uses light-sensing electronics to precisely detect the vibration of something as subtle as a musical string or even a tiny filament.
And what's truly ingenious is how it achieves this, right? By removing any magnetic pressure or pull on a metal string.
Exactly. It allows for a pure, unhindered vibration.
What's fascinating here is its non-contact nature. Unlike traditional pickups, this optical system doesn't physically interact with the string or the instrument's body.
Right, which is a huge advantage. Instead, it provides an incredibly flat and even response across the entire tonal range of the vibrating string.
This creates a sonic underpinning that precisely and accurately represents the instrument and, well, the performer too.
Because the string is free to vibrate naturally, engineers consider this one of the most influential and receptive techniques of string transduction ever developed.
Leading to a significant reduction in unwanted noise in the audio signal, I assume.
A huge reduction. It's a much cleaner signal.
To get a bit more technical then, the proprietary optical transducer at the heart of this system, it uses an infrared emitter.
Yes, an infrared emitter and an array of photodetectors for each string. The emitter essentially casts a shadow of the string onto these photodetectors.
Oh, okay, I see.
As the string vibrates, the dimensions and form of this shadow change slightly. This slight alteration in the shadow then changes a specific current that bypasses the photodetectors, producing an analog electrical signal that precisely represents the vibrating string.
Wow. It's a clever way to translate physical movement into an electrical signal without any physical contact.
It really is quite elegant.
So when we talk about light wave systems, we're really talking about a complete communication system.
Fundamentally, yes.
And like any effective system, it has core components. If we look at a general block diagram of an optical communication system, it consistently breaks down into three main parts.
Always these three. There's a transmitter, a communication channel, and a receiver.
And each of these plays a vital role, I imagine.
Absolutely critical. The transmitter is where the initial information, whether it's data, audio, or video, gets converted into an optical signal.
So turning electrical signals into light pulses.
Basically, yes. The communication channel, often fiber optics, but sometimes just free space, is the medium through which this light signal travels. Think of it as the highway for the light.
Makes sense.
And finally, the receiver detects the optical signal at the other end and converts it back into an interpretable form, back to an electrical signal usually.
So it's a complete loop for sending information using light.
Exactly. A closed system.
Now, let's zoom out to something truly grand, something that encompasses all these individual light systems, the electromagnetic spectrum, or EM spectrum.
Ah, yes, the full range.
This is the entire range of all types of electromagnetic radiation.
Yeah.
When we talk about radiation in this context, we just mean energy that moves and spreads out, traveling through space, right?
Precisely. It's not always the scary kind. Think about the visible light from a lamp in your house or the radio waves coming from a broadcast station. Those are both familiar forms of electromagnetic radiation.
Okay.
The EM spectrum is incredibly vast, and it includes many other types of radiation you might encounter every day, often without even realizing it.
It spans everything from high-energy gamma rays
All the way down to low-energy radio waves, including microwaves, infrared light, ultraviolet light, and X-rays in between.
And each segment has unique properties, different wavelengths, and distinct applications.
Completely different behaviors and uses, yeah.
Let's walk through them. Starting at the highest energy, we have gamma rays.
Very energetic.
You might encounter them when doctors use gamma ray imaging to see inside the human body, providing critical diagnostic information.
Right, for certain scans. But the most significant source of gamma rays in the universe is, well, the universe itself, from really violent cosmic events like supernovae or merging neutron stars.
Wow. Moving down in energy, we hit microwaves.
More familiar territory. Beyond heating your popcorn in minutes, astronomers use microwave emissions to study the structure and distribution of nearby galaxies.
How they're formed and interact.
Exactly. It lets us see the cold gas and dust. It reveals how they are formed and interact over cosmic time.
Next is infrared. Think about night vision goggles.
A classic example. They pick up the infrared glow produced by our skin and body heat, allowing us to see in complete darkness.
And in space.
In space, infrared glow helps scientists map the dust between stars, revealing nurseries where new stars are forming, which are otherwise hidden from view by visible light.
Fascinating. Then there's visible light, which is, well, what our eyes perceive.
The tiny sliver we're attuned to. Fireflies, light bulbs, and stars all produce visible light, allowing us to see the world around us in its full color and detail.
Radio waves are what your radio captures from broadcast stations, bringing you your favorite music or news.
Yep, the long wavelength end. But did you know that radio waves are also naturally produced by stars and other cosmic phenomena talking to each other across vast distances in space?
Like a cosmic conversation. That's amazing.
It really is. It's like a cosmic conversation, revealing processes we couldn't see otherwise.
Further up in energy from visible light, we find ultraviolet UV radiation.
These are famously produced by the sun, of course, and are responsible for skin tans and sunburns.
We all know about that.
Yeah. In space, very hot objects like young, massive stars also emit powerful UV radiation, giving us clues about their composition and evolution.
And finally, we have X-rays.
Higher energy still. Dentists use X-rays to image your teeth, helping identify cavities or other issues.
And airport security uses them to scan through your bags, ensuring safety.
Right. And just like UV, extremely hot gases in the universe also emit X-rays, providing insights into extreme cosmic phenomena like black holes and galaxy clusters.
It truly is a universe of light, most of which we can't even see, yet optical engineers leverage every part of it.
Every single part, yeah. It's all information.
Here's where it gets really interesting. Let's talk about the photoelectric effect. This is a profound phenomenon in physics that underpins so much of modern technology.
Absolutely fundamental.
Simply put, under specific conditions, light can actually provide enough energy to push electrons, freeing them from the surface of a material.
It's like light is knocking them loose. This process is called the photoelectric effect, and sometimes photoemission. Materials that can demonstrate this are said to be photoemissive.
And the ejected electrons are called photoelectrons, but it's important to remember they are fundamentally identical to all other electrons in every way, right?
Identical. Same mass, same charge, same spin, same magnetic moment. They're just electrons that happen to be kicked out by light.
The photoelectric effect was first observed way back in 1887 by Heinrich Hertz.
That's right, famously during experiments with a spark gap generator, which was an early form of radio receiver.
Hertz noticed that he could increase the sensitivity of his apparatus by illuminating it with visible light, or what were then called Roentgen rays.
Now known as X-rays?
Exactly. Later studies by J.J. Thomson in 1897 decisively showed that this augmented sensitivity was a direct result of light impacting and ejecting electrons.
And this phenomenon was absolutely crucial because it helped reveal the particle-like nature of light, a cornerstone of quantum mechanics.
Showing that light isn't just a wave.
But also comes in discrete packets of energy called photons. It was a revolutionary discovery, really pushed forward by Einstein's explanation in 1905.
Shifting gears, let's talk about how light actually bends. When light travels from one transparent medium to another, say from air into water, it usually changes direction or refracts.
It bends.
The law of refraction gives us a precise method to predict the amount of that bend. This law is a bit more complex than the one for reflection.
Slightly, yes. But understanding refraction is absolutely crucial for our conversation about lenses and their countless applications.
It's also famously known as Snell's law.
Named for Wilbrod Snell, who discovered it, or at least formalized it, back in 1621.
Just like with reflection, refraction also involves the angles that the incident ray and a refracted ray form with the normal, that imaginary line, perpendicular to the surface where the light hits.
Correct. Unlike reflection, however, refraction depends heavily on the properties of the two media through which the light rays are traveling. This dependence is made explicit in Snell's law via the refractive index of each material. The refractive index is a constant number for a given material and wavelength.
It essentially tells us how much a medium slows down light.
Exactly, and thus how much it bends it. The larger the difference in refractive indices between two materials, the more the light will bend when it crosses the boundary.
So if light bends, what happens if it bends too much?
That leads us to total internal reflection. This is a truly fascinating case of refraction that occurs when light moves from a medium with a higher refractive index to one with a lower index.
Like light trying to go from water into air.
Perfect example. The light ray can actually bend so much that it never leaves the original medium. Instead, it gets entirely reflected back inside. It essentially gets trapped.
How does that work?
Well, if we send a ray of light from water, a higher index medium 1.33, to air, a lower index medium 1.0, the light ray will be reflected back into the water if it strikes the surface at a sufficiently large angle.
There's a specific critical angle, right?
Precisely. This is the incident angle for which the refracted angle would be exactly 90 degrees, meaning the light would travel precisely parallel to the surface, just skimming along it.
Okay.
Any incident angle greater than this critical angle will, as a result, be entirely reflected from the boundary instead of being refracted through it.
So for water to air, you said any angle larger than about 48.6 degrees won't escape the water.
That's right. It just reflects back down. It's why you can sometimes see reflections at the bottom of a pool or lake when looking up from underwater, even if the surface is perfectly clear.
And this principle is fundamental to fiber optics.
Absolutely crucial. Light is guided along the core of an optical fiber by continually undergoing total internal reflection at the boundary between the core and the cladding, which has a lower refractive index.
Moving from the abstract to the incredibly personal, let's explore our very own optical system. The human eye.
Our biological camera.
It belongs to a common group of eyes found in nature called camera-type eyes, and the analogy is quite striking, just as a camera lens focuses light onto film or a sensor.
A sophisticated structure in our eye, the cornea, focuses light onto a light-sensitive membrane called the retina.
The eye itself is a slightly asymmetrical globe, roughly an inch in width, protected within the bony socket of your skull.
And when you look in a mirror, you can see its external components. The iris, which is the pigmented part that gives your eyes their unique color.
The cornea, that clear, transparent dome over the iris.
The pupil, the black circular opening in the iris that cleverly lets light in.
The sclera, which is the tough, white outer layer.
And the conjunctiva, a thin, transparent layer of tissue covering the front of the eye, except for the cornea itself. These parts work in concert even before light reaches the inner mechanisms.
So how does this incredible system actually work to transform light into vision? It all starts when light rays reflect off an object in your environment and enter your eyes through the cornea.
Right. The cornea, being the transparent outer cover, immediately gets to work, bending or refracting these incoming rays as they pass through the pupil's central opening. It does the bulk of the focusing.
Then the iris, that colored portion of the eye, takes control. It acts like a camera's aperture.
Exactly like one. Precisely opening and closing its muscles to make the pupil larger or smaller, regulating the exact quantity of light passing through.
The light rays then pass through the lens, which is uniquely dynamic, unlike a fixed camera lens.
Our eye's lens constantly changes its shape, becoming thinner or thicker, to further curve the light and focus it precisely onto the retina at the back of the eye.
That ability to change focus is called accommodation, right?
That's the term, yes, accommodation.
And the retina is truly where the magic happens. It's a thin layer of tissue at the very back of the eye, densely packed with millions of tiny light-sensing nerve cells.
Photoreceptor cells. These cells are specialized and differentiated by their shapes and functions into two main types: rods and cones.
Okay, rods and cones.
Cones are primarily concentrated in the very center of the retina, in a region called the macula. They are responsible for your clear, sharp central vision, your ability to perceive vibrant colors, and discern fine details, especially in bright light.
So cones are for detail and color in good light. What about rods?
Rods, on the other hand, are located outside the macula and extend all the way to the outer edge of the retina. They excel at providing peripheral or side vision, sensing movement, and are crucial for seeing in dim light and at nighttime.
But they don't perceive color.
No, they're essentially colorblind. They give you monochromatic vision in low light.
And the final critical step is that these specialized cells in the retina convert the light energy into electrical impulses.
That's the transduction step. The optic nerve then acts as a superhighway, sending these impulses directly to the brain,
which then processes them into the coherent, meaningful image you perceive. It's an incredibly complex and rapid translation.
Astonishingly fast and complex, yes.
Our eyes are packed with a whole array of supporting structures that are absolutely essential to sight, working tirelessly behind the scenes.
They really are intricate machines. For instance, various components manage fluid transport, like tears for lubrication and blood for nourishment.
And a network of 6 muscles controls each eye.
6 per eye, allowing for precise and rapid movement. Different parts protect the eye from damage, such as the eyelids and the outer layer of the cornea, the epithelium.
And many act as vital messengers, rapidly transmitting sensory information to the brain,
including the pain-sensing nerves in the cornea that warn of injury, and of course the optic nerve, which carries all the visual data from the retina. That's a whole integrated system.
Delving deeper into some of these key components, the cornea is not just the outermost coating. It's actually responsible for roughly 2/3 of the eye's total focusing power.
That's a huge amount. It has 5 distinct layers. The outer layer acts as a resilient shield and possesses remarkable self-repair capabilities from minor abrasions.
While deeper layers provide structural reinforcement.
Exactly. Strength and shape.
The pupil is that familiar black circle in the middle of your eye, and its main purpose is to precisely control the quantity of light entering.
It contracts in bright light to prevent overpowering the sensitive retina and expands in dim light to gather as much available light as possible, maximizing what you can see. Simple, but effective.
The iris is the colored part of your eye, and it functions as the sophisticated mechanism that regulates the pupil's size through its intricate muscles,
which either constrict or expand based on the prevailing light conditions. It's an automatic reflex.
The lens, positioned just behind the pupil, is crucial for allowing your eyes to focus on fine details, like the words on a page or the intricate patterns on a distant leaf.
And it's in a constant state of alteration, dynamically becoming thinner or thicker to adjust its focal length.
However, with age, the lens gradually loses much of its elasticity, often leading to common conditions like cataracts.
Where the lens becomes cloudy, yes. And presbyopia, making it difficult to focus on close objects. Happens to most people eventually.
Then we have the vitreous humor. That's the gel-like substance.
Correct. It fills the space between the lens and the retina, crucial for helping to maintain the eyeball in its accurate spherical shape.
This is also the region where those common floaters can originate.
Yes, as tiny portions of the vitreous humor clump together, casting subtle shadows onto your retina. Mostly harmless, but sometimes annoying.
With age, the vitreous humor naturally begins to shrink, which can sometimes cause more serious problems like retinal detachment or tears.
If it pulls too strongly on the retina as it shrinks, that needs prompt attention.
The retina, as we discussed, is the critical light-receiving tissue at the back of the eye. It receives all that incoming visual information and translates it into electrical signals,
which it then transmits directly to the brain for interpretation via the optic nerve.
And finally, the sclera, the white, tough outer layer of the eye, primarily offers strength, structure, and defense against external damage.
It's also filled with tiny blood vessels that can provide an eye physician with a surprising amount of information about your general health. Things like redness or vessel changes can indicate systemic issues.
Reflecting the interconnectedness of your entire body. Fascinating.
It really is.
Moving to how we quantify vision, visual acuity is a numerical measure that indicates the sharpness or clarity of your vision.
Right. For example, a visual acuity measurement of 20/70 vision means that a person with this level of sight, standing 20 feet from an eye chart, sees what someone with unimpaired, or 20/20 vision can clearly see from 70 feet away.
It's a direct comparison to what is considered normal vision.
Exactly.
We're all familiar with the Snellen chart, that classic eye chart with rows of letters of increasingly smaller size used to test vision.
So standard test. Normal vision is defined as 20/20, meaning the test subject sees the same line of letters at 20 feet that a person with normal vision sees at 20 feet.
If you have 20/40 vision, for instance, it means you must be at 20 feet to see what a person with normal vision can see at 40 feet.
Correct. It's a simple yet effective way to categorize visual sharpness.
Our field of view is remarkably wide. The peripheral, or side vision of the human eye, for instance, covers approximately 90 degrees horizontally.
Roughly, yes. The typical field of view for an individual human eye, when measured from the fixation point, the precise point at which your gaze is directed, is quite comprehensive.
How wide is it?
It extends about 60 degrees upward, 60 degrees nasally towards the nose, 70 to 75 degrees downward, and an impressive 100 to 110 degrees temporally, away from the nose and towards the temple.
For both eyes combined, the total visual field is massive, 130 to 135 degrees vertically and up to 200 degrees horizontally.
A huge panoramic view.
Huh.
What's particularly interesting is that when you view objects at large angles, the iris and pupil appear to be rotated towards you, the spectator.
Why is that?
It's due to the optical properties of the cornea and the aqueous humor within the eye. As a consequence, the pupil may still be noticeable, even at angles greater than 90 degrees.
There's also a specific area called the optic nerve, often referred to as the blind spot.
Yes, located about 12 to 15 degrees horizontally from the center of vision and 1.5 degrees below level. It's approximately 7.5 degrees high and 5.5 degrees wide.
And it's where the optic nerve leaves the eye, meaning there are no light-sensing cells there.
No rods or cones. So you literally can't see anything that falls precisely on that spot, though your brain usually fills in the gap seamlessly.
In terms of dynamic range, the retina boasts an impressive static contrast ratio of around 100,000 to 1.
Which translates to about 6.5 f-stops in photographic terms. That's quite a range it can handle at any given instant.
However, as soon as the eye shifts, these rapid eye movements are called saccades, it immediately readjusts its sensitivity.
Both chemically, through changes in retinal pigments, and mechanically by regulating the iris and pupil size. It's constantly adapting.
Think about moving from a brightly lit room into a very dark one. Initial dark adaptation, where your eyes begin to adjust, takes place in about 4 seconds.
About 4 seconds of thoughtful, continuous darkness, yes. Full adaptation, involving deeper modifications in retinal chemistry, like the Purkinje effect.
That's where your vision shifts from cone-dominant color vision to rod-dominant monochromatic vision in low light.
Exactly. That's mostly complete in about 30 minutes. This process is highly nonlinear and comprehensive.
Meaning even a brief flash of light can disrupt it and force the adaptation process to start over again.
It resets the clock, essentially. And for full adaptation to occur, it's heavily dependent on good blood flow. Thus, dark adaptation can be hampered by poor circulation or even vasoconstrictors like tobacco.
Eye movement is crucial for clear vision. Why is that?
Because the visual system in the human brain is simply not designed to process information effectively if images are slipping across the retina at more than a few degrees per second. It gets blurry.
So to be able to see clearly while you are moving, your brain must constantly compensate for the movement of your head and skull by precisely rotating your eyes in their sockets.
Constant tiny adjustments.
Frontal-eyed creatures like humans have a small area of the retina with very high visual acuity called the fovea centralis.
Yes, this tiny spot captures about 2 degrees of your visual field, but it's where your sharpest vision comes from.
To get a clear, detailed view of the world, your brain must constantly turn your eye so that the image of the object you're staring at falls directly on this fovea.
That's why your eyes dart around constantly, bringing different parts of the scene onto the fovea. Any failure to make these precise eye movements
whether due to muscle issues or neurological problems.
Can lead to grave visual disabilities, significantly impairing a person's ability to navigate and interact with their environment.
And while we're on the subject of eye movement, rapid eye movement, or REM,
Classically refers to the sleep period during which the most vivid dreams typically arise. During this period, the eyes do indeed move quickly.
but it's important to note that this is not in itself an exclusive characteristic of eye movement.
Correct. Eyes also move rapidly when we are awake, during saccades, for instance. REM sleep movement is just one type.
Finally, controlling all this intricate movement are the extraocular muscles.
The powerhouse behind eye movement. Each eye is controlled by 6 distinct muscles that manage its activities. The lateral rectus, the medial rectus, the inferior rectus, the superior rectus, the inferior oblique, and the superior oblique.
6 muscles working together.
When these muscles exert differing tensions, a precise torque is applied to the eyeball, causing it to rotate in a remarkably pure rotation with only about 1 millimeter of displacement.
It's a beautifully orchestrated, incredibly precise system that allows us to direct our gaze with such fluidity.
Truly a marvel of biomechanics.
All right, let's transition from our amazing natural optical systems to the ingenious tools we've engineered to manipulate light. We're moving into part 2, focusing on optical elements and how they craft images.
Okay, engineered optics.
Starting with mirrors and prisms, the mirror is quite possibly the oldest optical component we've intentionally used.
Polished-looking glasses have been found in Egyptian pyramids constructed as far back as 1900 BC. That's ancient tech.
Today, plain or flat, mirrors are virtually everywhere, from your bathroom to complex laser setups.
Ubiquitous. But beyond simple reflection, spherical or parabolic mirrors are often used in optical systems as powerful alternatives to lenses, especially in telescopes.
It's important to remember that when a ray of light hits a surface, only the portion of the visible spectrum that is reproduced or reflected is what we actually see.
The rest is either absorbed or transmitted through the material. Reflection is selective.
What's truly fascinating is how white light, which contains all colors, interacts with materials like glass or water.
Dispersion. As incident white light enters a transparent medium, each of its constituent wavelengths, meaning each color, is bent according to the material's refractive index.
But here's the key. This refractive index isn't constant for all wavelengths. It's wavelength dependent.
Exactly, causing the shorter wavelengths, like blue light, to bend more than longer wavelengths, like red light.
This phenomenon, called dispersion, means the colors emerging from a prism travel along separate paths and appear in the order of increasing wavelength,
creating that familiar rainbow effect. The prism doesn't generate the colors, it simply reveals what was already present in the white light by separating them.
So a mirror, at its core, is an optical component that has a highly reflective surface.
That's the defining feature. This surface can be on top of a substrate, like glass, which is what we call a front surface mirror.
Or the reflective surface can be on the back of a transparent substrate known as a rear surface mirror, like your everyday bathroom mirror.
Precisely. For visible light applications, the reflecting surface is commonly aluminum or silver. Infrared mirrors, however, often use a gold reflective exterior because gold reflects infrared light more efficiently.
And just like lenses, many front surface mirrors have a thin protective coating, or glaze, to shield that delicate reflective surface.
Yes, protection against scratches and oxidation is crucial, especially for aluminum and silver.
Now let's talk about some specialized mirror applications. Plate beam splitters.
Very useful components. They are frequently used to allow both illumination and viewing or imaging down the same optical path.
Like a microscope vertical illuminator.
Exactly. Light for viewing the sample travels through the beam splitter, reflects off the sample, and then the image light reflects off the beam splitter towards the detector or eyepiece.
So the light encounters the beam splitter twice, once during its transmission to the sample and once during its reflection back.
That's right, which affects efficiency. The optimal efficiency for a plate beam splitter is actually only 25%.
Only 25%.
Yes, and this occurs with a 50.50 beam splitter, meaning it nominally reflects 50% and transmits 50%. Half the light is lost on the way in, and half of what returns is lost again.
Okay, that makes sense.
This maximum efficiency is quite flat. Even a 60.4 or 40.60 split will give you around 24% efficiency, and an 80.20 split still yields 16%.
So the slightly lower accuracy of a perfect 50.50 split isn't a major concern in terms of overall light management for their intended purpose?
Not usually, no. Their value lies in combining or splitting light paths conveniently, not necessarily in maximizing total light throughput.
Then there are pellicles. A pellicle is essentially a very thin, flexible membrane that acts as a beam splitter.
Yes, typically consisting of a 2 to 5 micrometer thick casing, usually made of nitrocellulose, stretched tautly across an extremely flat metal ring. Sometimes it's even covered for protection.
A pellicle is thin enough that, at least in terms of transmitted light, the optical distortions or aberrations it introduces are typically small enough to be disregarded.
Generally, yes. It's surprisingly robust mechanically, provided nothing directly punctures or hits the delicate membrane.
Pellicles are particularly useful because they significantly reduce something called eidolon fringes or interference fringes.
Right. Those subtle, often rainbow-like patterns you can sometimes see when light reflects back and forth between two very close, parallel surfaces.
By making the pellicle incredibly thin, these fringes are effectively spread out so much that they become imperceptible.
Exactly, ensuring a clean image. This thinness also means its optical properties are much less sensitive to temperature changes, which is critical for precision systems.
Moving on to flat mirrors. They are theoretically the simplest optical elements available and often the simplest to utilize effectively.
High-quality flat mirrors are readily available at low cost for a broad variety of wavelengths from many suppliers. However, there are three major practical considerations when using them.
Okay, what are they?
First is alignment sensitivity. Even minor misalignment can lead to misdirection of the beam or incredibly costly errors in larger optical systems. It has to be perfect.
Second, errors like thumbprints or dust.
Right. Mirrors are often more sensitive to contamination than lenses and can be more challenging to clean without scratching their delicate reflective coating.
And the third.
Fundamentally, a flat mirror, or a flame mirror, is used to adjust the direction of a light ray, but not its deviation or focus. It simply bounces light. You need to remember it doesn't change the convergence or divergence.
Here's where it gets really interesting. A curved mirror, a spherical mirror specifically.
Yes, a round mirror can take a collimated beam of light, meaning rays traveling perfectly parallel to each other, and focus that light at a single point.
Which we call the focal point, often denoted by F.
Correct. The distance between the mirror and this focal point is called the focal length of the mirror, symbolized by F. For a spherical mirror, the focal length is precisely half of the radius of curvature, R, of the mirror surface.
Conversely, if you place a source of light exactly at the focal point,
It will produce a perfectly collimated beam of light after the rays reflect off the curved mirror surface. This is how spotlights and car headlights often work.
an off-axis spherical mirror can be used in designs so that the light path of the collimated beam isn't blocked by the light source itself or other components.
Yes, it allows you to get the source out of the way. Curved mirrors can be either parabolic or hyperbolic too.
How do they differ?
Similar to a spherical mirror, a parabolic mirror forms a perfectly collimated beam of light if a light source is situated at its focus, often with less aberration than a sphere. A hyperbolic mirror can uniquely focus a beam from one focal point to another, which is useful in certain telescope designs like Cassegrains.
Let's shift our focus to prisms. Custom optical prisms are precision-crafted to perform diverse functions, ranging from simple light redirection to complex image manipulation.
And they can be made to either extreme precision, with very tight tolerances for high-end applications, or to commercial quality for a wider range of everyday uses.
In optical manufacturing, there are many types of prisms, each serving a unique purpose.
Oh, loads. Standard Lodge prisms, roof prisms, laser dispersing prisms, pentagon prisms, right-angle prisms, various types of beam splitters like non-polarizing cube beam splitters, corner cube prisms, rhomboid prisms. The list goes on.
What's fascinating here is how prisms create color components. We mentioned dispersion earlier.
Right. Well, information from Asia in the early 1600s indicated that prisms were recognized for their ability to produce colors. It was Sir Isaac Newton who famously explained that the prism did not generate the colors.
It merely made visible the components already present within white light through dispersion.
Exactly. This happens because each color or wavelength of the spectrum has a slightly different speed when passing through the glass, and therefore its own unique refractive index, causing it to bend at a slightly different angle.
As a result, the colors separate and emerge from the prism in order of increasing wavelength, creating that beautiful spectrum.
Separating the light out.
Delving into specific prism types, glass prisms are indeed used for separating light into its color spectrum, but more frequently they are employed for beam steering and image manipulation.
Both of these functions typically involve internal reflection of one or more faces of the prism. These reflections can be either Total internal reflection, where the light strikes the surface at an incident angle greater than a specific critical angle and is completely reflected internally.
Or a more conventional reflection from a mirror-coated exterior surface.
Correct. Which type is used depends entirely on the specific application, the angles involved, and the design requirements.
Right angle or Porra prisms are commonly used for steering a light ray through approximately 90 degrees.
Their optical performance is quite similar to a simple flat mirror positioned in the same way relative to the prism's hypotenuse. Light typically enters normal to one face, bounces off the hypotenuse, either through total internal reflection or by means of a reflective coating, and then exits through the third face.
This arrangement is frequently employed in microscopes and binoculars.
Very common in binoculars, yes. In microscopes, too, where prisms are more easily integrated and clean than mirrors, and where their high efficiency and consistent spectral performance are significant advantages.
Another benefit is that the thick optical element is usually contained entirely within the optical path.
Whereas a mirror's thick substrate would extend outside it, it can make for a more compact design.
What's fascinating here is the roof prism. Most standard prism categories are frequently modified by replacing one of their faces with a roof.
Essentially, a pair of exterior surfaces set at precisely 90 degrees to one another. The result is optically equivalent to cementing a right-angle prism, hypotenuse first, onto the top of a normal prism.
This unique configuration introduces an additional left-right inversion to the image.
It does. The most common type is the Amici roof prism, which is a right-angle prism with a roof. It had the incredibly useful property of precisely routing a light ray through 90 degrees without inverting the image left to right,
making it crucial for binoculars and other imaging systems where you want an upright, correctly oriented image.
Absolutely. In high-precision imaging applications, the roof prism must be manufactured with extreme care, as any imperfection along the roof edge will appear as a noticeable line right in the center of the image. Very tight tolerance.
The Dove prism is an image-rotating prism that also inverts the image left to right.
It has a distinctive quadrilateral cross-section, and its faces are cut at a specific Brewster's angle relative to its central axis. Light propagates down the axis, is refracted at the entrance face, undergoes a single internal reflection off one side, and then exits through the other face, being refracted back to axial propagation.
Crucially, if the prism is physically rotated about its axis, the image it produces rotates at twice the rate of the prism's rotation.
Double the speed. This unique property makes it useful in applications where precise image rotation is required, such as in certain types of periscopes or scientific instruments for derotation.
Then we have specialized prisms like equilateral, Brewster, and litro prisms, a rhombus prism,
which has two parallel faces, is commonly used for light dispersion, separating white light into its constituent colors, like in a spectroscope.
For applications involving polarized light, the use of a Brewster prism is often preferred.
Yes. In this type of prism, the light enters and exits at or near Brewster's angle, an angle at which light with a particular polarization is completely transmitted without reflection, making it ideal for managing polarized beams, like inside lasers.
The pentaprism is an image-erecting prism that maintains a stable 90-degree deviation between the incoming and outgoing light rays,
independent of their precise angle of incidence. That's the key benefit.
How does it achieve that?
The physical basis is two reflections that occur within a single plane, similar to how a Porra prism functions. The light beam undergoes two reflections from internal surfaces that are at a precise 45-degree angle to one another.
Unless the prism is made of an extremely high refractive index material, total internal reflection is impractical.
Right. The incidence angle is too shallow, so these reflecting faces are usually silvered. Both the entry and exit facets are normal to the ray path, meaning pentaprisms can introduce slight interference patterns known as etalon fringes, but they don't exhibit much chromatic aberration or color bending.
Interestingly, there's nothing particularly special about only achieving 90 or 180 degrees of deviation when it comes to other constant angle prisms.
No, the only requirement is to have two reflections from internal surfaces that are precisely held together at a fixed angle.
For instance, to create a 60-degree stable deviation, you can utilize a 30, 60, 90-degree prism.
Exactly. You direct the light ray in near normal to the short face. It will then reflect off the hypotenuse by total internal reflection and subsequently off the long side. Finally, it exits through the hypotenuse at normal incidence, deviating by exactly 60 degrees.
The incidence angle on the extended surface is only 30 degrees, so it must be silvered unless the refractive index n is greater than 2.0.
Correct, to ensure that second reflection actually happens and isn't refracted out.
A wedge prism is used for performing small angular deviations up to perhaps 20 degrees in the path of a light beam.
Just a slight nudge to the beam direction. Two such identical wedges, when mounted coaxially and made separately rotatable, can be used to point a light ray anywhere within a 40-degree half-angle cone.
Except for a very small zone around 0 degrees.
Right near the center, yes. This setup for steering light is significantly more compact and robust than using two mirrors, but it's generally less convenient to adjust precisely, and like all refracting optical strategies, it's more susceptible to producing etalon fringes.
Okay, let's connect all this talk about light and optical elements to how we actually see the world. We're moving into image formation,
How we create pictures with light?
which is essentially the study of how two-dimensional descriptions of three-dimensional objects are shaped. In the realm of digital imagery, this process also includes the crucial steps of analog to digital conversion and sampling.
Turning continuous light into discrete pixels, yeah.
What's truly fascinating here is the image formation in the human eye and its incredibly dynamic lens. The principal difference between the lens of our eye and a conventional optical lens.
Like in a camera, is that our eye's lens is supple. It's wonderfully flexible.
The curvature of the front surface of the lens is slightly greater than the curvature of its back surface.
Yes. The shape of the lens is precisely controlled by the tension in tiny fibers connected to the ciliary body. To focus on distant objects, this muscular strength causes the lens to be relatively flattened and thinner.
Conversely, this strength allows the lens to become thicker and more curved in order to focus on objects close to the eye.
That's accommodation again. This constant adjustment happens effortlessly most of the time.
So the focal length of the eye, the distance between the optical center of the lens and the retina, dynamically contrasts from about 17 millimeters when viewing distant objects to approximately 14 millimeters when focusing on very close objects.
As the refractive power of the lens increases from its minimum to its maximum, yes. When your eye focuses on an object farther away than about 3 meters, the lens exhibits its lowest refractive power.
When your eye focuses on a near object, the lens becomes most powerfully refractive.
This constant automatic adaptation is a marvel of biological engineering, allowing us to see clearly across a vast range of distances without consciously thinking about it.
Now let's consider plane mirror image formation. An image is formed by a plane mirror as light emanates from an object in a multitude of directions.
Some of this light reaches the mirror and reflects according to the fundamental law of reflection. Angle of incidence equals angle of reflection.
Each of these reflected light rays can then be traced backward, seemingly originating from a point behind the mirror where they all appear to converge or intersect.
This point is the image position. Anyone positioned along the path of one of these reflected rays will perceive the image as a virtual representation of the object, as if the light were truly coming from behind the mirror. It's not physically there, but it looks like it is.
We've also seen how images are shaped through the reflection of rays off curved mirrors. The point where all the reflected light rays actually converge or appear to come from is known as the image point.
It's not simply the point where light rays meet. It's also the point where reflected light rays appear to an observer to be originating from. Regardless of where the observer is positioned, they will see a ray of light passing through the actual image location.
To clearly view the image, the observer must align their gaze with the image position in order to perceive the representation via the reflected light rays.
The diagram you might imagine shows rays from the object reflecting from the mirror and converging at the image position. The reflected light rays then begin to spread out again, with each one capable of contributing to the perception of the object's image. This applies to real images formed by converging mirrors.
Moving to lenses, converging lenses have the unique ability to form both real and virtual images.
This is a key distinction from diverging lenses, which can only create virtual images. The process through which images are formed for lenses is similar in principle to the process for mirrors.
Images are shaped at locations where any viewer perceives them when looking at the object through the lens.
So if the path of several light rays from a point on an object is traced through a converging lens, all these light rays will converge and intersect at a single point after being refracted by the lens, forming a real image if the object is outside the focal point.
On the other hand, diverging lenses always generate virtual images.
Always. This is because the refracted light rays do not actually converge to a single point. Instead, they spread out.
Imagine a light bulb.
Right. The incident rays from the bulb pass through the diverging lens, refract, and then spread out, reaching different observers. The image position is where these refracted rays appear to interconnect if traced backward.
But since the refracted light rays do not physically exist at that image position, the image is said to be a virtual representation.
It only materializes to an observer as though light were emanating from this virtual point and entering the observer's eye. It's always smaller and upright.
This conversation relates to the formation of an image by a point object, like a tiny idealized light bulb. But the identical principles apply to objects that exist across multiple points in space, like a person.
Absolutely. As you look at a person through a lens, light emanates from each individual point on that person in all directions. Some of this light reaches the lens and refracts.
The outcome is that all the light originating from one individual point on the object will refract through the lens and converge or appear to converge at one solitary point on the image.
This holds true for all points on the object. Light from every tip on the object intersects to generate a representation of that specific point. The consequence is that a faithful reproduction or likeness of the entire object is shaped as we look at it through the lens.
This replica or similarity is the precise image of that object.
Assuming the lens is reasonably well corrected for aberrations, yes.
Now, when it comes to optical instruments, their main purpose is often to make things appear larger or to reveal finer details.
When you use an optical tool, whether it's something as simple as a magnifying glass or more complex like a telescope or microscope, you're frequently trying to make things look better, meaning larger or clearer, so you can more easily discern fine details.
One crucial rule to remember about this is that if you want to make objects seem bigger, you're always going to utilize converging mirrors or lenses.
Always converging elements for magnification. Diverging mirrors or lenses, in contrast, will always produce smaller or reduced virtual images.
Many practical optical systems, such as sophisticated microscopes and telescopes, use multiple lenses to form images.
Very common. To analyze any system with more than one lens, you work in steps. Each lens takes an object and creates an image.
The initial object is the object for the first lens, which then generates its image. That first image then effectively becomes the object for the subsequent lens.
And so on, building the final image step by step through the system. The image of one becomes the object for the next.
Let's take the microscope as a classic example. A basic microscope is typically made up of two converging lenses, an objective lens close to the sample and an eyepiece lens close to your eye.
Correct. One key reason for using two lenses rather than just one is that it's much easier to achieve higher overall magnification.
If you want a total magnification of 35x, for instance, you can use one lens to magnify by a factor of 5 and the second lens by a factor of 7.
Exactly. This cascaded approach is normally much simpler to design and manufacture than trying to achieve that entire 35x magnification from a single very powerful lens.
The first lens, the objective, generates a real magnified image,
which then serves as the object for the eyepiece lens. And that second lens then further magnifies it to produce the final, usually virtual image you'd see when you look through the microscope.
Telescopes also require at least two lenses, often more.
Minimum of 2 for a refracting telescope. This is because you use a telescope to look at objects extremely far away, objects that appear very small to the naked eye.
The first lens, called the objective lens, creates a tiny, real image very close to its focal point.
The telescope is then designed so that this real inverted image formed by the objective lens is positioned just slightly inside the focal length of the subsequent lens, the eyepiece.
As with the magnifying glass, this arrangement then produces a highly magnified virtual image.
Correct. This final image is also inverted compared to the original object.
For astronomical telescopes, where you're looking at stars or planets, this inversion doesn't typically matter.
No, astronomers don't usually care if Jupiter looks upside down. However, if you're observing something on Earth like wildlife, you usually want an upright image,
which can be achieved by adding a third lens or a prism system to reinvert the image.
Yes, like the poro or roof prisms we discussed earlier, often used in binoculars for that purpose.
This raises an important question for any optical system: resolving power.
The ability to see fine detail. The resolving power of an optical device, whether it's your eye or a powerful telescope, is its ability to separate two distinct, distant objects that are very close together into clearly discernible individual images.
As opposed to appearing as a single blurry compound image.
Exactly. For example, if you look at two stars in the night sky, they might appear as one to the naked eye. However, through a telescope, you can often see that they are, in fact, two separate stars.
Because the telescope has higher resolving power.
Much higher. So why does the telescope separate the stars into distinct objects when your eye cannot? It's all because of a fundamental wave phenomenon called diffraction.
Diffraction is the bending of waves as they pass around obstacles or through small openings.
That's it. Light waves, like all waves, diffract, and this imposes a fundamental limit on how small a detail an optical system can resolve. Bigger apertures generally mean better resolving power, less diffraction blurring.
And speaking of diffraction, X-ray diffraction is another fascinating application, leveraging this very principle.
A hugely important technique. Naturally occurring structures that act much like a finely arranged diffraction grating are crystals.
Many solid materials like common salt, graphite, diamonds, and most metals have a crystal arrangement where their atoms are precisely arranged in a repeating, ordered, three-dimensional pattern.
A crystal lattice, yes. This is effectively a three-dimensional version of a diffraction grating.
Atoms in a typical solid are separated by distances of only an angstrom or a few angstroms.
Tiny distances, 0.1 nanometers or so. This atomic spacing is much smaller than the wavelength of visible light.
However, X-rays have wavelengths that are roughly the same size as these atomic spacings.
Yes, on the order of angstroms. Therefore, X-rays interact with crystals in a way extremely similar to how visible light interacts with a finely ruled grating, producing distinct diffraction patterns.
By analyzing these patterns, scientists gain invaluable insights into the precise atomic and molecular structure of crystalline materials.
Absolutely. It's a technique crucial for fields ranging from materials science and geology to biology and drug discovery. It lets us map out where the atoms are.
Let's move into our third part, where we control light and delve into the material science that makes it all possible. We'll start with apertures and stops.
The gates of light. Essentially, these control how light enters and moves through an optical system.
When we talk about these, we distinguish between two crucial elements: the aperture stop,
Which is the physical opening that limits the quantity of light reaching the imaging region, typically exemplified by the adjustable diaphragm near the front of a complex camera lens.
and then there's the field stop.
Which is the physical opening that limits the size of the object that can be imaged or the field of view.
These two elements work in tandem to precisely control not only how much light is captured, but also what portion of a scene is ultimately rendered.
Without them, optical systems would be flooded with unfocused light or capture unintended parts of the scene. They define the beam.
So an aperture in optics is simply a gap or an opening through which light passes. More specifically, the aperture and focal length of an optical system collaboratively determine the cone angle of the light rays that converge to a point in the image plane.
Apertures are primarily used to limit the amount of light exposed to imaging sensors or photodetectors for a range of laser or imaging applications.
Preventing oversaturation or even damage to the sensitive components.
Exactly. Too much light can be bad. These apertures come in various types, including adjustable irises, fixed pinholes, or narrow slits, all meticulously designed to block specific portions of a light source from reaching the photodetectors.
What's fascinating is their adaptability. Apertures can be precisely adjusted by increasing or constricting the width or breadth of the gap to suit manifold applications or lighting environments,
Offering flexible control over light throughput. You can find these commercially from suppliers like Edmund Optics, and some are available in mechanical or physical wheel options for multiple customization.
They can even be placed directly in front of an imaging sensor for superior efficiency and augmented mobility.
Or within the lens sister itself, like a camera diaphragm.
Lenses often come with specifications for their maximum and minimum apertures, typically expressed as F numbers, for instance, f1.4, f2.2.
In this example, f1.4 represents the greatest opening, meaning the widest diameter, and f22 represents the least opening, the smallest diameter.
The maximum aperture tends to be of most interest and is always highlighted when describing a lens because this value is also known as the lens speed.
Right. It directly affects the exposure time required to capture an image. A faster lens, a lower f number, lets in more light, allowing for shorter exposure times or shooting in dimmer conditions.
The amount of light admitted through an aperture is proportional to the square of its diameter,
And thus inversely proportional to the square of the f number. This means that an aperture of f2, for example, allows for exposure times that are 1/4 that of f4. Each full stop changes the light by a factor of 2.
This relationship is a crucial concept for photographers, astronomers, and anyone working with light-sensitive systems.
Absolutely dictates how much light can be gathered and how quickly.
When we consider aperture area, the total quantity of light captured by a lens is directly proportional to the area of the aperture.
Makes sense. Bigger hole, more light. Interestingly, the precise focal length value isn't strictly necessary when directly comparing the light-gathering power of two lenses that have a similar angle of view. A value of 1 can be used instead for simplification.
The key takeaway is that the light collected is primarily proportional to the reciprocal square of the f number, n.
Yes, light gathering goes as 1n nano. This means that if two cameras, despite having different sensor sizes and focal lengths, manage to achieve the same angle of view and have the same aperture area, they will actually collect the same total quantity of light from a scene.
However, the resulting focal plane luminance, how bright the image appears on the sensor, would depend solely on the f number n.
Correct. So it would be less bright in the camera with the superior arrangement, larger sensor, longer focal length, and a higher f number, assuming both lenses have equal light transmissivity. It's a subtle but important distinction between total light gathered and perceived brightness at the image plane.
Finding the optimal aperture for a given optical system or photograph is always a delicate balance.
A trade-off. It depends equally on the inherent optics, specifically the trade-off between depth of field and diffraction, and on the overall performance characteristics of the lens itself.
Optically, as a lens is stopped down, meaning its aperture is made smaller, increasing the f number, the blur due to defocus at the limits of the depth of field, DOF, decreases.
So things further from the focus point get sharper. However, simultaneously, the blur caused by diffraction increases.
Because the light is being squeezed through a smaller opening and bending more.
Exactly. The presence of these two opposing factors implies that there's an optimal point at which the combined blur spot, and thus the overall image blur, is minimized.
At that point, the f number is ideal for maximizing image sharpness for a given depth of field.
It's the sweet spot. A wider aperture, or a lower f number, allows more light, but causes additional defocus blur for objects outside the precise focal plane. Conversely, a narrower aperture, or a higher f number, increases the depth of field, but causes additional diffraction blur, which limits overall sharpness.
It's truly about finding that balance where these competing optical effects are optimized for the sharpest possible image.
So the specific needs of that shot or system, yes.
Reaffirming the concept, stops have a limiting effect on the imaging process through the dimension of the clear opening within an optical system.
And this limiting effect depends crucially on the position of that stop, or limiting diameter. The physical opening that determines the quantity of light which reaches the imaging region is called the aperture stop.
Clearly exemplified by the adjustable diaphragm found near the front of a complex camera lens.
And, as mentioned before, the physical opening that controls the ultimate size of the object that can be imaged is called the field stop.
Adjustable stops are typically crafted from thin metal leaves that can be moved to precisely control the quantity of light reaching a film or CCD detector.
For example, a laboratory stop might be used to define the exact amount of light that arrives at an adjustable slit for diffraction studies. Such sophisticated arrangements are also precisely used in cameras to set the f-stops for exposure alteration.
Giving photographers immense control over their images.
Absolutely.
The interplay between apertures and f-stops is fundamental to photography and many optical designs. An adjustable metal leaf arrangement is typically positioned after the first few elements of a complex camera lens.
To precisely regulate the quantity of light that ultimately reaches the film or the digital CCD detector, it is common practice to indicate the size of the opening in this aperture stop in terms of the f-stop or f number.
The f-stop is simply defined as the focal length of the lens divided by the effective diameter of the aperture.
That's the formula. It is evident from this relationship that a higher f number implies a smaller aperture diameter for a given focal length lens.
Since a circular aperture has an area, so A equals vol, doubling the aperture width and consequently having the f number will admit 4 times as much light into the system.
4 times the light. This inverse square relationship is vital for understanding exposure and light gathering. Going from f4 to f2.8 doubles the light. f2.8 to f2 doubles it again.
Now let's talk about f-stops and depth of field, a crucial concept for anyone trying to master focus in optics. Increasing the f-stop by 1 stop, meaning halving the aperture area.
Actually, halving the diameter roughly corresponds to doubling the f number, which quarters the area light. Let's say increasing the f number, like going from f4 to f5.6. This has the immediate side effect of necessitating you to slow down the shutter velocity by 1/2, or increase ISO to maintain the same exposure.
Okay, Less light means longer exposure, but it provides the significant benefit of greatly increasing the depth of field of the formed image.
Right. By depth of field, we mean the range of distances within the image where objects appear to be acceptably in sharp focus.
While perfect sharpness is a theoretical ideal, there is a practical depth range within which the image appears piercingly focused to the human eye.
And that depth of field significantly increases with a higher f number, smaller aperture. Common full stops in photographic lenses include f1.4, 2, 2.8, 4, 5.6, 8, 11, 16, 22, and 32.
You'll notice cameras often have additional numbers, like third or half stops, between these full stops, allowing for even finer control.
But the underlying principle remains constant. Smaller aperture, greater depth of field, but also more diffraction eventually.
Just to quickly recap on aperture stops, it's the physical opening that restricts the quantity of light that passes through an optical system.
Like the camera diaphragm, the quantity of light admitted is precisely controlled by the diameter of this diaphragm aperture, which is indicated on the camera by the f number or f-stop number.
Effect. Smaller opening reduces light but increases depth of focus.
Correct.
And for field stops, recap. It's simply the element that restricts the dimension or angular width of an object that can be imaged by the system.
For cameras, the physical dimension of the film, or the CCD detector itself, determines the maximum image dimension and thus serves as the field stop, defining the boundaries of what can be captured in your frame.
Lastly, in this section, we come to pupils, which are essentially virtual openings.
A slightly more abstract concept, yes. The core idea here is that the effective dimension of a stop within an optical system may be larger or smaller than its actual physical size.
And this variation is due to the refractive action of the lenses themselves.
Precisely. Officially, a pupil is defined as an image of the aperture stop, as seen from a particular viewpoint.
The entrance pupil is defined as the image of the aperture stop, as seen by an observer looking into the front of the lens from the object side.
Through any optical elements that precede the stop. If the physical aperture is positioned behind the lens, you'll find that more light will effectively pass through that physical opening than would have if the lens were not present.
Because the lens gathers light from a wider angle and directs it towards the aperture.
Exactly. Tracing the predicted path of a chief ray, one that is refracted by the lens so that it just passes through the edge of the aperture without the lens, shows you that the entrance pupil is the larger, effective opening that would be necessary to pass that same chief ray in the absence of the lens. It's where the light appears to be limited from the object's perspective.
The exit tupil of an optical system is similarly defined as the image of the aperture stop, as seen by an observer looking back into the lens from the image plane.
Right. For example, if the physical aperture stop is positioned in front of the lens, then the exit pupil is the image of that aperture stop, as seen from the image plane, looking back through the lens. In this specific case, the entrance pupil is simply the physical opening itself, since there are no optical elements preceding it from the object's perspective.
It's a complex but elegant concept that helps designers understand and manipulate light paths more completely.
Ensuring optimal light collection and image formation, and also determining things like eye relief and eyepieces, it's where you need to place your eye to see the full field.
Let's delve into photometry and radiometry, the fascinating sciences of measuring light, both seen and unseen.
Quantifying light. Radiometry is the scientific discipline of examining and quantifying light across any part of the entire electromagnetic spectrum.
In practice, the term is frequently limited to the precise measurement of infrared, visible, and ultraviolet light using specialized optical instruments.
That's where most practical measurements happen, yes. It encompasses both rigorous theory and practical application.
The practical side of radiometry involves a wide array of scientific instruments and resources used to calculate light.
Highly sensitive thermopiles, photodiodes, bolometers, photosensitive films and emulsions, vacuum phototubes, and charge-coupled devices, CCDs, among many others. Lots of ways to detect photons.
The theory of radiometry, once understood, is quite straightforward.
Relatively speaking, yes. For example, the power per unit solid angle per unit projected area is described as radiance, denoted by L. It is measured in watts per steradian per square meter, WSRM/RM.
This quantity depends significantly on both the area of the light source and its orientation relative to the observer, using the projected area, ds-cos.
Right, because the power received depends not only on the size of the surface, but also on its direction. A surface tilted away looks smaller. The total power received from a source over a given surface, ESI, is called irradiance, E, measured in William attrate. That's power per unit area falling onto a surface.
So let's quickly list some core radiometric quantities in SI units to give you a sense of how we break down light energy.
Good idea. Energy E, the total amount of light energy, is measured in joules J.
Radiometric power, P or A, often referred to as radiant flux, represents the rate at which light energy is flowing.
Measured in joules per second or watts W, it's the flow rate of energy.
Radiant excitance, M, is the power emitted from a surface per unit area.
Measured in William M, how much power is leaving.
And radiant intensity is the power emitted by a source per unit solid angle.
Measured in WF, it tells you how bright a source is in a particular direction, and it can also have an angular dependence, meaning the light might be brighter in some directions than others. Think of a spotlight versus a bare bulb.
Radiant energy is, at its essence, light as a form of radiant power. Electromagnetic radiation, which can be considered both a wave and a particle.
Depending on how you measure it, yes. It transports energy through space. When light is absorbed by a physical object, its energy is converted into several other forms.
For instance, a microwave oven heats a glass of water when its microwave radiation is absorbed by the water molecules.
The radiant power of the microwaves is converted directly into thermal power, or heat.
Likewise, visible light causes an electric current to flow in a light meter when its radiant power is transferred to the electrons as kinetic energy,
creating a measurable signal. Radiant energy, denoted as Q, is measured in joules.
Radiant flux is simply energy per unit time, which we calculate in joules per second, or watts. Think of a laser beam.
It has a certain number of watts of radiant power. Because light flows through space, radiant power is more commonly referred to as the time rate of flow of radiant power, or more simply, radiant flux. It's the total power of light being emitted or transmitted per second.
Then there's radiant flux density, which precisely quantifies the radiant flux per unit area at any point on a surface, whether that surface is physical or purely imaginary.
Right. There are two primary circumstances. The flux can be incoming at the surface, in which case the radiant flux density is referred to as irradiance. E, defined as E, is d by A.
Where A is the radiant flux inward at the point, and dA is the infinitesimal area surrounding that point.
Alternatively, the flux can be departing from the surface due to emission and/or reflection. This is referred to as radiant exitance, M, defined as M yield AdA, where MA is the radiant flux departing the point.
The significance is that radiant flux density can be calculated anywhere in three-dimensional space.
On the exterior of physical objects, in the space between them, or within transparent media. Radiant flux density is measured in watts per square meter.
Radiance is most clearly understood by first visualizing it. Imagine a tiny ray of light incoming at or departing from a point on a surface in a very specific direction.
Radiance is simply the minuscule quantity of radiant flux contained within this ray, per unit area, per unit solid angle. A more formal description requires us to think of a ray as being an infinitesimally thin elemental cone with its apex at a point on an actual or imaginary surface. This cone has a differential solid angle, DO, that is measured in steradians.
Radiance tells us how much light power is flowing through a specific area in a particular direction. It's like directional brightness.
Exactly. It's a very fundamental quantity in radiative transfer.
And finally, radiant intensity. We can imagine an infinitesimally small point source of light that produces radiant flux equally in all directions.
Radiant intensity represents the amount of radiant flux emitted in a specific direction, confined within a rudimentary cone. It's measured in watts per steradian, WSR, and tells you how strong a point-like source is in a particular direction.
Now let's pivot to photometry, which is the fascinating science of measuring visible light. Crucially, it does so in units that are biased or weighted according to the sensitivity of the human eye.
This is the key difference from radiometry. It's a quantitative discipline based on a mathematical model of the human visual response to light. That is, our perception of brightness under carefully controlled conditions.
The human visual system is a spectacularly complex and highly nonlinear detector of electromagnetic radiation, with wavelengths ranging from approximately 380 to 770 nanometers.
We perceive light of different wavelengths as a range of distinct colors across the visible spectrum. For example, 650 millimeters is red, 540 millimeters is green, and 450 millimeters is blue, and so on.
What's truly fascinating is how our eyes perceive light. We don't see all colors with equal brightness.
Not at all. Our vision sensitivity varies significantly by wavelength, with sensitivity peaking in the green at around 550 millimeter. This standard curve is called the V lambda curve.
This isn't just a biological quirk. It's a fundamental insight that optical engineers use every day.
Absolutely. It's why, for instance, green lasers appear much brighter than red ones of the same radiometric power, or why emergency exit signs are often green. Our eyes are simply optimized to pick up those wavelengths, making them stand out even at lower intensities.
It's a core difference between measuring pure light energy, radiometry,
Right.
and measuring perceived brightness, photometry.
Measuring what the eye actually sees.
Let's break down the photometric quantities in SI units. The power of emitted radiation is generally calculated in joules. However, if the wavelength of the emitted radiation lies specifically within the 400–700 millimeter range,
The visible range. Then this power is uniquely described as luminous energy, and its unit is the Talbot, though you don't hear that one very often. More common are the flux units,
okay, the photometric equivalent of irradiance is a luminance, E.
calculated in lumens per square meter or lux, as LX. This measures how much perceived light falls on a surface, like the brightness of your desk under a lamp.
The photometric equivalent of radiant flux is luminous flux, whose units are lumen. Yeah.
Yes, this is the total perceived power of light emitted by a source, like the lumen rating on a light bulb.
The photometric equivalent of radiant intensity is luminous intensity.
Measured in lumens per steradian or candela, CD. The candela was once known simply as the candle, and luminous intensity was historically called candle power. It measures the perceived brightness of a source in a specific direction.
A source that consistently emits 4 lumens, or 12.57 lumens, in all directions from an isotropic uniform source would produce 1 LMS, or 1 candela, in any given direction.
Correct. For example, a typical 100-watt incandescent light bulb provides approximately 1,700 lumens of visible power. If this light were evenly distributed in all directions, its luminous intensity would be about 135 candela, though they rarely are perfectly even.
Luminous excitance M is the photometric equivalent of radiant excitance, calculated in lumens per square meter. This measures the total luminous flux emitted or reflected from a surface area.
And luminance L is the photometric equivalent of radiance, calculated in candela per square meter or lumens per steradian per square meter. This is the property of a source or surface that is commonly referred to as brightness, though the unit for L used to be the Lambert. It's the perceived brightness of an extended surface.
The historical roots of luminous intensity are fascinating, going back to Pierre Bouguer in 1729.
Yes, in his groundbreaking work, L'Essai d'Optique, Bouguer discussed photometric measurements in terms of the most convenient light source of his time, a standard wax candle.
These wax candles then became the basis of the point source concept in photometric theory, with wax candles themselves being used as national light source standards throughout the 18th and 19th centuries.
Hard to believe now, but that was a standard for a long time.
Luminous flux, also known as luminous power, is the photometrically weighted radiant flux power. Its unit of measurement is the lumen.
Precisely defined as 683 watts of radiant power at a frequency of 540 by 10^8 hertz, which is 555 millimeter green light, the peak of human eye sensitivity under bright conditions.
As with luminous intensity, the luminous flux of light at other wavelengths can be determined by referring to the CIE photometric curve,
which maps the eye's standard sensitivity across the visible spectrum. For an isotropic source, a point source that emits light uniformly in all directions, with a consistent luminous intensity of 1 candela, it will produce precisely 1 lumen of luminous flux per unit solid angle, or steradian. Total flux is 4 times the intensity for an isotropic source.
Luminous energy is simply the photometrically weighted radiant energy, and it is measured in lumen seconds.
Right, flux integrated over time. Then there's luminous flux density, which encompasses 2 related quantities, illuminance and luminous excitance. This is the photometrically weighted radiant flux per unit area.
Illuminance is the photometric equivalent of irradiance, measuring the total luminous flux incident on a surface per unit area.
Whereas luminous excitance is the photometric equivalent of radiant excitance, measuring the total luminous flux leaving a surface per unit area due to emission or reflection.
Luminous flux density is typically measured in lumens per square meter, lux, though a foot candle is an older unit equivalent to 1 lumen for each square foot.
Still used sometimes in the U.S. lighting industry.
Finally, luminance itself is the photometrically weighted radiance. In terms of visual perception, we recognize luminance as an estimated measure of how bright a surface appears when we view it from a specified direction.
Luminance used to be described as photometric brightness. But this expression is now avoided in illumination manufacturing because the subjective impression of visual brightness is influenced by many additional physical, physiological, and psychological factors beyond just the light itself. Things like glare, adaptation state, context.
So luminance is the objective measure, while brightness is subjective.
Exactly. Luminance is precisely measured in lumens per square meter per steradian, or candelas per square meter, also called nits.
Now let's explore the very building blocks of optical systems, the optical materials themselves.
The stuff lenses and mirrors are made of. Optical materials is also the name of a peer-reviewed technical periodical focusing on the design, synthesis, characterization, and application of properties suitable for a wide variety of optical devices.
Suppliers like Newport offer a broad diversity of lenses made from various materials, each with unique characteristics.
Including BK7, UV-grade fused silica, infrared-grade calcium fluoride, CF2, magnesium fluoride, MgF2, AMTR, and zinc selenide, just to name a few common ones.
The selection of the right material is absolutely crucial and depends heavily on the specific wavelength of light being used and the desired performance needs of the optical system.
Critical choice. For instance, for applications in the visible and near-infrared spectrum, up to about 2.1 micrometers, BK7 offers excellent performance at a high-quality value.
However, in the ultraviolet region, especially down to 195 nanometers, UV-grade fused silica is a superior choice due to its transparency in that range.
Much better UV transmission, yes.
Let's dive into some detailed material properties, starting with BK7. This is one of the most common borosilicate crown glasses used for visible and near-infrared optics.
It's highly valued for its excellent homogeneity, meaning its properties are uniform throughout its very low bubble content and inclusions, and its relatively easy manufacturability. Good all-rounder.
These qualities make it a high-quality, cost-effective option for transmissive optics, which are optics that light passes through.
BK7 is also comparatively hard and exhibits good scratch resistance, making it quite durable for many applications.
The primary transmission range for BK7 is from 380 to 2100 nanometers, covering much of the visible and near-infrared spectrum.
It's generally not recommended for temperature-sensitive applications, such as high-precision mirrors, because its refractive index can change noticeably with temperature. Not the most stable.
While offering excellent transmittance through the visible and near-infrared spectrum, it can still transmit down to 350 nanometers in the ultraviolet.
It starts absorbing significantly below that. For most typical optical glass components, or when optical glass is generally specified for custom elements, BK7 stands as a standard, high-performance choice due to its balance of properties and cost.
Next, UV-grade fused silica. This is an artificial, amorphous, meaning non-crystalline, silicon dioxide of tremendously elevated purity.
This unique non-crystalline silica glass combines an incredibly low thermal expansion coefficient, meaning it contracts very little with temperature changes, with excellent optical clarity and outstanding transmittance in the ultraviolet region.
Making it transparent down to 195 nanometers.
Even lower with special grades, down into the deep UV. Its superior transparency and homogeneity surpass those of natural crystalline quartz, without the issues of directional dependency, birefringence, and thermal instability inherent in crystalline forms.
For these reasons, fused silica is preferably used with high-energy lasers due to its elevated laser-induced damage threshold.
It can handle a lot of power. UV-fused silica also exhibits outstanding transmittance in the visible and infrared regions up to about 2.1 micrometers, and boasts a very low inclusion content with high refractive index homogeneity.
It's widely used for both transmissive and reflective optics, especially where high laser damage resistance or UV performance is critical.
Or thermal stability, yes. Very versatile high-performance material.
Then we have CuF2, or calcium fluoride. This is a cubic single crystal material, meaning its atoms are arranged in a repeating 3D lattice.
Typically grown using the vacuum stock barger method, a specialized process for graying large, pure crystals. CuF2 offers good vacuum UV to infrared transmission, possessing a wide spectral range.
It's an outstanding choice for deep UV to infrared applications because of its non-birefringent property.
Yes. Being cubic means light behaves the same regardless of polarization direction, which simplifies things. It boasts transmission above 90% between 0.25 and 7 micrometers, making it incredibly versatile.
It is frequently used for excimer laser optics due to its low absorption and high damage threshold.
Handles those powerful UV pulses well. Material for infrared applications can also be grown using naturally mined fluorite, which offers a much lower cost, though purity might be lower.
However, KF2 has a very poor thermal property, a high coefficient of thermal expansion.
Yes, it expands, contracts a lot with temperature, and its refractive index changes significantly too, so it should be avoided in high operating temperature environments or where stability is key.
Calcium fluoride can often be used without an anti-reflection coating due to its naturally low index of refraction.
Relatively low index, yes, reduces surface reflection somewhat. One important note is that this material is gently hygroscopic, meaning it absorbs some moisture from the air. Not great for humid environments or water immersion.
Another important material is MgF2, or magnesium fluoride. This is an optically positive birefringent crystal.
Meaning light travels at different speeds depending on its polarization and direction within the crystal, unlike KF2. It's also grown using the vacuum stock-barger technique, ensuring high purity.
MgF2 offers good transmission from vacuum UV down to infrared. It's typically oriented with its C-axis parallel to the optical axis of the system.
To minimize the effects of its birefringence in applications where that's undesirable, like lenses, if you need birefringence, like in a wave plate, you orient it differently.
MgF2 is another excellent choice for deep UV to IR regions with a good transmission range from 0.15 micrometers to 6.5 micrometers.
Its established use in fluorine environments makes it ideal for lenses, windows, and polarizers used with excimer lasers. MgF2 is also highly resistant to thermal and mechanical shock and boasts a superior laser-induced damage threshold.
It's also notable for being one of the lowest refractive index infrared materials available,
which makes it very useful as an anti-reflection coating material itself, often the outer layer in multi-layer coatings due to its durability and low index.
Crystal quartz, naturally occurring, optically positive, uniaxial birefringent single crystal.
Usually grown by a hydrothermal process to achieve the necessary purity and size for optical applications. It exhibits good transmission from the vacuum UV range all the way to the near-infrared.
Due to its inherent birefringent property, its ability to split light into two different polarized beams, crystal quartz is typically used for specialized components like wave plates or polarizers.
Exactly. Not usually used for simple lenses because the birefringence would mess up the image. You use it when you specifically want to manipulate polarization.
Then there's Pyrex, a well-known borosilicate glass, a trade name by Corning. It stands out for its low coefficient of thermal expansion and superior resistance to heat shock.
Meaning it can withstand rapid temperature changes without cracking. Think ovenware. It is mostly used for non-transmissive optics, such as mirrors.
Due to its slight homogeneity variations and higher bubble content compared to optical-grade glasses.
Right. It's not clear enough or uniform enough for high-quality lenses usually, but it's great for mirror substrates or windows where imaging quality isn't paramount. It can be used as an alternative for shot bore float in most cases.
And its robust nature allows it to be precisely machined, CNC milled, cut, lapped, and drilled to various measurements, forms, or surface finishes.
Yes, it's quite workable.
To give you a practical sense of its properties, Pyrex has a thermal coefficient of expansion of 32.5 x 10 eries per degree Celsius.
Which is low compared to regular glass, but much higher than fused silica or zero-do. It has an annealing point of 560 degrees C, a softening point of 821 degrees C, and a strain point of 510 degrees C.
Mechanically, its density is 2.23 grams per cubic centimeter. Its Knoop hardness is 448 kJ/mm, making it quite resistant to scratching.
Its Young's modulus is 64 GPa, and its Poisson's ratio is 0.2, and optically its refractive index is 1.473 at 589.3 nanometers.
Chemically, it offers excellent hydrolytic resistance, acid resistance, and alkali resistance,
making it durable in many environments. Electrically, its dielectric constant is 4.6. Resistivity is high. Dielectric strength is 0.5 kV/mm. A good, stable, general-purpose glass for non-imaging optics.
Moving on, Zero-Dur, a specialized glass ceramic material that has an incredibly low coefficient of thermal expansion, approaching zero.
Almost zero expansion. This, combined with exceptional homogeneity of this coefficient throughout the entire piece, means it barely expands or contracts even with significant temperature fluctuations.
This makes Zero-Dur supreme for mirror substrates where extraordinary thermal stability is necessary.
Think large astronomical telescopes, satellite optics, semiconductor lithography equipment, wherever ever pointing or focus stability is absolutely critical over temperature changes.
However, Zero-Dur should not be used for transmissive optics.
No, it's opaque or at least translucent due to the ceramic microcrystals within the glass matrix. It's strictly for reflective applications, usually mirrors.
Finally, Zinche, or zinc selenide. This is a material produced by a chemical vapor deposition process and is commonly used in thermal imaging and medical systems.
Zinc is an exceptional choice for infrared lenses, thanks to its broad wavelength range from 600 nanometers all the way up to 16 micrometers, covering most of the important thermal IR bands.
Zinc has a high refractive index, which usually necessitates an anti-reflection coating to achieve high performance.
Yes, its high index means significant reflection losses, around 17% per surface, without coatings.
What's fascinating here are its practical considerations. Zinc is moderately soft with low scratch resistance.
You have to be careful with it. It's not recommended for use in harsh environments where it might get scratched or abraded. Extra caution is necessary during its handling, treatment, and mounting.
Despite these limitations, ZNES is considered the most excellent choice for optics used in high-power CO2 laser systems.
Yes, because of its very low absorption coefficient at the 10.6 micron CO2 laser wavelength and high resistance to thermal shock, it can handle intense laser energy without deforming or damaging, provided it's clean.
When it comes to the reflectance of optical materials, it's important to understand that all metal reflectors, like those made of aluminum or silver,
Will slowly degrade when exposed to an impure environment, such as air with pollutants, moisture, or fingerprints. Oxidation and contamination reduce reflectivity.
cumulative exposure to strong ultraviolet emission also negatively affects their performance, and overheating of the reflective surface will permanently damage the reflector.
UV can break down some protective coatings, and excessive heat can cause the thin metal layer to blister or change structure. These factors highlight the need for protective coatings or controlled environments for high-performance mirrors.
For measurement techniques of optical material properties, a UV-NIR spectrophotometer is an indispensable tool.
It can accurately calculate both the transmittance, how much light passes through, and reflectance, how much light bounces off, spectrum of a material over a wide range of wavelengths.
From the near-infrared region all the way to the ultraviolet.
Exactly. For example, a UV 3700 UV-VIS NIR spectrophotometer can be used to measure the transmission range of a compact disc substrate or the reflectance range of silicon wafers.
This instrument allows for non-destructive measurement of even extremely large samples and performs spectrophotometric analysis across a broad wavelength range from the ultraviolet to the infrared.
By using specialized light sources and detectors with minimal absorption in the deep ultraviolet DUV range, along with nitrogen purging to remove atmospheric absorption, oxygen and water-absorbed UV, it permits precise measurements across a wide wavelength range from 165 to 3300 nanometers, even with DUV-specific models, essential for characterizing materials.
Let's delve into aberrations, which are, in essence, the imperfections that arise even in perfectly manufactured optical systems.
The bane of the lens designer. An optical aberration is a deviation of an optical system's performance from the ideal predictions of paraxial optics.
In an imaging system, it occurs when light from a single point on an object does not perfectly converge to or diverge from a single sharp point after passing through the system.
That's the definition. An optical aberration fundamentally results in a distortion or blur in the image formed by an optical system compared to the original object.
These imperfections can happen for a number of reasons, including the inherent limitations of optical mechanisms such as lenses and mirrors, specifically their shapes.
What's crucial to understand is that aberrations are errors in an image that arise because of the fundamental physics of light and the geometry of the optical system, not necessarily because of manufacturing defects.
Even ocular devices made of the finest materials with no flaws can still produce aberrations.
Absolutely. These aberrations are typically classified into two main types. Monochromatic aberrations, which occur when imaging with a single wavelength of light.
And chromatic aberrations, which occur when imaging with two or more wavelengths, because the refractive index varies with wavelength.
Right. Color fringing is the classic example of chromatic aberration.
Let's explore some common types of aberrations, specifically the monochromatic ones that affect systems using a single color of light. First, spherical aberration.
The most basic one occurs most prominently in lenses with simple spherical surfaces. Rays of light passing through the outer regions of a lens, farther away from the central axis, are refracted more strongly than those passing closer to the axis.
This results in the rays focusing at different points along the optical axis.
Correct. Rays that make a small angle with the optical axis and travel close to it are called paraxial rays, and they typically focus further from the lens. Rays that interact with the edges of the optical element are called peripheral rays.
And when a wavefront is spherically aberrated, these peripheral rays focus earlier than the paraxial rays.
Yes, closer to the lens. The difference between where these two types of rays converge to a focal point is a key way to calculate the severity of spherical aberration in a system. It leads to a blurry spot instead of a sharp point.
What's fascinating here is coma. While spherical aberrations describe where different points focus along the optical axis.
Coma describes the specific and peculiar appearance of an image formed by an off-axis object point. Spherical affects on-axis points too, but coma is inherently off-axis.
The image of a single point of light that lies off the optical axis will form a characteristic teardrop or comet-shaped image rather than a neat spot.
Exactly, hence the name coma. The tail or flare of this comet-shaped image often points away from the axis, but it can also sometimes lean towards it, depending on the specific lens design and stop position.
This aberration significantly degrades the image quality, especially at the edges of the field of view.
Makes stars look like little comets near the edge of a telescope image, for example.
Then there's astigmatism. This aberration also occurs when an object point is positioned off-axis.
Yes. Rays produced from such an object point form a spherical cone as they travel towards a lens. When this off-axis object point hits the lens surface, this cone of rays forms an ellipse, not a perfect circle, on the surface of the lens.
If the cone of rays had been produced from an on-axis object point, they would have formed a perfect circle on the lens's surface.
Correct. Astigmatism causes light rays from different planes, essentially, rays in the plane containing the object point and the axis, versus rays perpendicular to that plane to focus at different distances.
Resulting in two separate focal lines rather than a single sharp point.
Yes, often called the tangential and sagittal foci. Optical designers refer to the tangential plane, which contains both the optical axis and the object point, and the sagittal plane, which is perpendicular to the tangential plane. Focus is different in these two orientations.
Field curvature, or curvature of field, is an aberration that is related to astigmatism, but it can exist independently in a system that doesn't suffer from astigmatism.
Yes, you can correct astigmatism, but still have a curved focal surface. In the case of field curvature, the object is imaged on a bowed or curved surface, the Petzval surface, rather than a flat plane.
The important thing to note is that the image is not inherently indistinct or blurry due to this aberration. It is just projected onto a curved surface.
Exactly. The focus might be sharp, but it's sharp on a curve. This presents a significant difficulty for devices like cameras and slide projectors, as their film or sensor plane needs to be perfectly flat for a sharp image across the entire frame.
Fortunately, a curved image field can often be flattened or compressed by using a clever combination of different lenses or specific lens shapes within the optical system.
Yes, using field flattener lenses is common in high-quality systems like telescopes and microscopes.
And finally, distortion. Similar to field curvature, an image suffering from distortion is also not indistinct or blurry.
Right. Instead, the image points are displaced fundamentally from their ideal positions, those predicted when paraxial rays are traced through the optical system. The magnification changes across the field of view.
This means the image points may be repositioned either towards or away from the optical axis.
Correct. The crucial implication is that different parts of the object experience dissimilar magnification, leading to a warped appearance. Straight lines in the object become curved in the image.
There are two main types. Pincushion distortion,
which makes straight lines bend inward towards the center, causing the representation of a square to appear stretched at the corners like a pincushion, common in telephoto lenses.
And barrel distortion,
which makes straight lines bend outward, pushing the corners of a representation of a square inward towards the middle, like the sides of a barrel, common in wide-angle lenses. Both types alter the shape of the image without necessarily blurring it.
Moving to chromatic and monochromatic optical aberrations more broadly. Optical systems are typically initially designed and calculated using first-order or paraxial optics
to determine basic image size and position. It's vital to remember that paraxial optics is a simplified model and does not account for aberrations. It treats light as a simple ray and thus omits the wave phenomena that cause these imperfections.
Optical aberrations are named and differentiated in several ways. For simplicity, we can consider them alienated into two groups. Chromatic aberrations,
which are present when using more than one wavelength of light,
and monochromatic aberrations, which are present even with a single wavelength of light.
Like the 5 sidal aberrations we just discussed: spherical, coma, astigmatism, field curvature, and distortion.
Chromatic aberrations are further classified into two types, transverse and longitudinal.
Longitudinal chromatic aberration can then be main or minor. Transverse chromatic aberration, PCA, happens when the size of the image changes with wavelength.
In other words, when white light is used, different wavelengths like red, yellow, and blue focus at slightly different positions in a perpendicular plane, leading to color fringing at the edges of objects.
Yes, the magnification is different for different colors. You see colored edges, especially away from the center. Longitudinal chromatic aberration occurs when different wavelengths focus at separate points along the optical axis itself.
For example, red, yellow, and blue wavelengths might focus at distinct distances from the lens.
Exactly. Blue light usually focuses closer to the lens than red light for a simple positive lens. In optical context, specific wavelengths are often referred to as C light, 656.3 nanometers red, D light, 587.6 nanometers yellow, and F light, 486.1 nanometers blue.
These descriptions often arise from their characteristic hydrogen production lines for CNF illumination and helium for deglow.
Yes, they act as standard reference points, Fraunhofer lines, for evaluating color errors and designing achromatic lenses.
By far, monochromatic aberrations outnumber chromatic aberrations. Consequently, they are often characterized and named using wavefront coefficients in addition to their more common surnames.
For example, spherical aberration has a wavefront coefficient of W040. This wavefront coefficient arises from a mathematical framework, like Zernike polynomials, that describes the actual difference between an ideal, perfect wavefront and the aberrated or distorted wavefront produced by the real optical system.
In the mathematical monochromatic equation, WM is the wavefront coefficient, h is the normalized image height, r the position in the pupil, and 3 is the angle between them.
It gets quite mathematical, describing the shape of the distorted wave. Once the wavefront coefficient is known, the order number of the aberration can be determined by adding L and K from the coefficient notation. However, this sum will always generate an even number.
Since optical aberrations are frequently referred to as first, third, fifth order, etc., if K plus L equals 2, it is a first-order aberration. If K plus L equals 4, it is a third-order aberration, and so on.
Correct. First order relates to basic focusing and magnification, paraxial optics. Third order includes the 5 sidal aberrations. Normally, only first and third order aberrations are essential for system analysis and correction in practical optical designs.
Higher order aberrations exist, but they are not usually corrected in optical systems because of the immense complexity this adds to the system.
Exactly. Frequently, the difficulty of accurately correcting higher order aberrations is simply not worth the marginal improvement in image quality, unless it's a very high performance system like in lithography.
It's crucial to reiterate in the comparison of optical aberrations that these are fundamental divergences from an ideal mathematical model.
It is important to note that they are not caused by any physical, optical, or mechanical flaws or defects in the manufacturing of the lens. You can have a perfectly made lens that still has aberrations.
Rather, they are inherent limitations caused by the very shape of the lens itself, or the arrangement of optical elements within a system, due to the wave nature of light and the approximations made in simple lens formulas.
Optical systems are typically calculated using first-order or paraxial optics in the initial design phase to compute basic image size and position. As we discussed, paraxial optics does not take into account aberration. It treats light as a simple ray, and so leaves out the wave phenomena that fundamentally cause these aberrations. Aberration analysis comes next.
Optically, identifying aberrations can be quite challenging, even with advanced computer analysis. Pinpointing exactly what aberrations are present in an optical system is not always an easy task.
As usually 2 or more aberrations are present simultaneously in any given system, complicating the analysis. They interact and mask each other.
Optical designers use a variety of sophisticated tools to identify aberrations and then attempt to correct for them.
Tools often include computer-generated spot diagrams, wave fan diagrams, and ray fan diagrams, modulation transfer function, MTF plots. Spot diagrams visually exemplify how a single point of light would appear after being imaged through the system, ideally a tiny dot, realistically a blurry blob.
Wave fan diagrams are plots that show the deviation of the actual wavefront relative to an ideal, perfectly flat, or spherical wavefront.
Exactly. They quantify the wavefront error directly.
For optical aberration examples, after an optical system is designed and manufactured, aberrations can be empirically observed by imaging a perfect point source, such as a laser, through the system.
You then examine how that single point appears on the image plane. Multiple aberrations can certainly be present, but in general, the more similar the resulting image looks to a perfect, tiny spot, the fewer the significant aberrations.
This holds true regardless of the size of the spot, as the spot might be magnified by the system but still retain its spot-like quality.
Correct. Engineers use visual references that demonstrate the ray performance if only one specific aberration were present, as well as reproductions of aberrated images seen through ordinary examination objectives, along with potential remedial actions to reduce or correct these aberrations. Experience helps a lot here.
Let's move into our final part, the art and science of optical system design. Here's where it gets really interesting, because it's not as straightforward as you might think.
No magic formula, unfortunately. There is no single, direct technique for designing truly unique optical systems from scratch. In other words, there's no certain step-by-step process that will lead you from a set of performance specifications directly to an appropriate novel design without relying on prior knowledge and experience.
However, when a designer recognizes that a certain type of existing design or pattern is inherently capable of meeting a given performance level,
It becomes a relatively straightforward process for a skilled designer to adapt and refine that existing plan to meet the new requirements using optimization software.
furthermore, even seemingly simple improvements or developments to available designs can almost always be achieved through well-established methods of optimization and refinement.
Yes, computer optimization is very powerful for tweaking existing designs.
Thus, it's clear that a significant part of a lens designer's toolkit consists of an intimate and thorough knowledge of a wide range of existing designs, their unique characteristics, their limitations, their quirks, and their potential.
Knowing the history in the classic design forms, Cook triplets, double Gauss, Petzval lenses, etc., is essential. Herein lies a crucial fraction of the art in optical design. Essentially, it consists of the designer's initial choice of where to begin.
A choice deeply informed by their comprehensive understanding of the design landscape.
Exactly. Choosing the right starting point is half the battle.
The advent of the electronic computer, in the course of little more than a decade, fundamentally revolutionized the techniques used by optical designers.
Massively. Previously, a designer had to resort to all manner of ingenious manual techniques, like graphical ray tracing or complex aberration theory calculations, to avoid tracing lots of exact rays.
Simply because of the immense time and effort involved in doing it by hand.
Hours per ray sometimes. But now, the computer has reduced ray tracing time by many orders of magnitude. It's practically instantaneous for thousands or millions of rays.
It is now far easier and faster to trace countless rays through an optical system than it is to speculate, infer, or hypothesize from incomplete or sparse data.
Much easier. A processor can even be made to carry out the entire design procedure from beginning to end, more or less without direct human interference, using optimization algorithms.
However, the results produced by such an automated procedure are nevertheless intricately dependent on the initial starting point chosen by the human designer, as well as the specific way in which the computer has been programmed to optimize.
Garbage in, garbage out still applies. The optimization needs guidance, constraints, and a good starting point. So an immense amount of art, if perhaps with somewhat less personal approval, is still present, even in the most mechanical and automated design methods.
The human touch in defining the problem and guiding the initial approach remains vital. Let's consider the simple meniscus camera lens. There are just two primary elements to work with in the design of a basic meniscus camera lens: the lens itself and the aperture stop.
If, for the moment, we limit ourselves to a thin lens with spherical surfaces, the key parameters we may choose or regulate are the material of the lens, its refractive index, its focal length, its shape or bending, the precise location of the stop, and the width of the stop.
With these degrees of freedom, the goal is to design a lens that will produce a satisfactory image on a specified size of film or sensor.
Which inherently implies that all the deviations or aberrations of the system must be kept acceptably tiny, or at least balanced.
The symmetrical principle is a core concept in optical design, offering a powerful shortcut.
Very elegant. In an optical system that is completely symmetrical, meaning the elements are arranged identically on either side of the aperture, stop coma, distortion, and lateral chromatic aberration are theoretically zero.
For true total symmetry, a system must function at unit magnification, meaning the image is the same size as the object, and the elements behind the stop must be perfect mirror images of those in front of the stop.
Those are the strict conditions.
This principle is of huge usefulness, not only for systems operating at unit magnification, but also for those operating at unlimited conjugates, meaning systems designed for very distant objects.
Yes, where light rays enter effectively parallel. This is because, even though distortion, coma, and sideways color, lateral chromatic aberration, are not entirely eliminated under these circumstances. They tend to be considerably reduced when the elements of an optical system are designed to be largely symmetrical.
For this reason, numerous lenses designed to cover substantial fields of view with low distortion and low coma tend to be generally symmetrical in their construction.
Like many camera lenses, especially standard or slightly wide ones, if we were to apply this principle to the simple meniscus camera lens, we would just employ two equal meniscus lenses centered symmetrically on either side of the stop.
The resulting lens would be practically free of coma, distortion, and lateral color. A design exemplified by the classic periscopic lens.
Yes, a very early symmetrical design. The hypergam lens, for instance, combined this symmetry with a thick meniscus principle to flatten the field, achieving a very remarkable astigmatic field correction of plus or minus 67 degrees. Huge field.
However, this impressive performance came at the expense of a heavily undercorrected spherical aberration, which limited its useful speed or maximum aperture to about f30 or f20.
Very slow lens, only usable in bright light, but incredibly wide and distortion-free for its time. Trade-offs again.
Moving to achromatic telescope objectives, let's look at their design through thin lens theory. An achromatic doublet designed to correct for chromatic aberration
Is typically composed of two elements: a converging lens made of crown glass, which has low dispersion, and a diverging lens made of flint glass, which has high dispersion.
Stated more generally, an achromatic doublet consists of a low relative dispersion element with the same sign of optical power as the desired doublet, and a high relative dispersion element with the opposite sign of optical power.
Correct. The powers and dispersions are chosen carefully, so the color errors cancel out, usually bringing two wavelengths, like red and blue, to the same focus. As degrees of freedom in design, we have the choice of glass type for each element, the optical powers of the two elements, and the specific shapes or curvatures of the elements.
For design forms of relatively unassuming lenses, those up to 3 or 4 inches in diameter, the cemented form is often preferred.
Where the two elements are glued together. This is chiefly because the precise alignment between the elements, regarding shared concentricity concerning the optical axis and freedom from tilt, can be more accurately upheld during the production process. Fewer surfaces to align.
An air-spaced achromat, sometimes called a dialite, can also be made achromatic.
But the degree of chromatic correction will typically vary with the object distance. It will be truly achromatic only for its intended design distance, making it less versatile for objects at varying distances. Cemented doublets are generally more stable in this regard.
What's fascinating here is a thermalization, which deals with maintaining temperature stability in optical systems.
Keeping things in focus when the temperature changes. When the temperature of a lens component changes, two primary factors influence its focus or focal length, and they often work against each other.
As the temperature rises, all the physical dimensions of the element increase. This, by itself, would tend to extend both the effective focal length and the back focal length of the lens.
Simple expansion makes it bigger and weaker. However, simultaneously, the refractive index of the lens material also changes with temperature. This is called the DNDT value.
For a lot of common optical glasses, the refractive index actually rises with increasing temperature.
Yes, which makes the lens stronger and tends to shorten the focal length. So you have physical expansion trying to lengthen the focal length, and the change in refractive index trying to shorten it.
The precise interplay of these two competing factors needs to be carefully managed and engineered for stable focus across varying temperatures.
Using combinations of materials with different thermal expansion coefficients and DNDT values, along with careful housing design, allows engineers to create a thermalized system that hold focus over a wide temperature range. Very important for military or aerospace optics.
Let's conclude our deep dive with the diffractive surface in lens design, which is all about precisely bending light with microstructures rather than just conventional refraction.
A newer, powerful tool. A diffractive surface, as used in modern lens design, is essentially a type of Fresnel surface, often described mathematically as modulo 2. In simpler terms, it is a special Fresnel surface, where the height of each tiny step or facet is engineered such that the light wavefront is precisely retarded or stepped by exactly one full wavelength relative to the adjacent step.
So the step height for a diffractive surface is typically calculated as un1, assuming the surface is bounded by air.
Where all is the design wavelength of light and n is the refractive index of the material. For a typical glass or plastic surface, where n is approximately 1.5, this translates to a step height of about 2 wavelengths of light. Very tiny steps.
This is in stark contrast to the much larger step heights, on the order of tenths of a millimeter or more, found in an ordinary plastic Fresnel lens used in overhead projectors.
Much, much smaller. The slope and precise shape of these tiny Fresnel facets can be defined by a sphere or an aspheric curve for complex light manipulation, especially correcting chromatic aberration. It's also worth noting that similar optical effects can sometimes be obtained by a localized variation of the refractive index within the material itself, creating a gradient index or GION lens rather than shaping the surface.
When it comes to diffraction efficiency, the term keniform specifies a diffractive surface that has perfectly smooth, curved facets,
Allowing for theoretically 100% efficiency in directing light at the design wavelength into the desired diffraction order. Even a linear or cone-shaped blazed grating, like in a shell grating, can achieve very high efficiency, like 99%.
A binary surface, on the other hand, approximates these ideal, smooth Fresnel facets by using a stair-step contour.
Like pixels approximating a curve. This stair-step shape is created through a high-resolution photolithographic process, similar to making computer chips, where the surface relief is precisely shaped by exposing photoresist through a sequence of multiple masks, building up the layers step by step. 2 levels gives 1 efficiency, 4 levels higher, 8 levels higher still, approaching the smooth keniform.
For manufacturability, it's clear that the longer the wavelength of light and the weaker the optical power of the diffractive surface, the wider and deeper are the steps, and consequently, the easier the fabrication task becomes.
Bigger features are easier to make accurately. The radial spacing, or the distance from one Fresnel step to the next, zone spacing, is approximately Rn 1 Presway.
Where r is the diffractive surface's radius of curvature, f is its focal length, and y is the radial distance from the optical axis.
The smallest spacing, which occurs at the edge of the diffractive lens, is approximately 2 Lg, where such as is the relative aperture, or f number, and Na is the numerical aperture. The total number of Fresnel steps or zones on a diffractive lens is approximately d day f, where d is the lens diameter. These formulas tell you how fine the features need to be.
Techniques used for fabricating these precise diffractive surfaces include single-point diamond turning,
which is especially effective for long-wave infrared materials like germanium or zinc selenide. Ion beam machining, where material is precisely removed by an ion beam, electron beam writing, and laser beam writing.
Photolithography, while tremendously challenging on curved surfaces, is highly successful on flat or plano surfaces.
Yes, easier to pattern flat wafers. For large commercial quantities, injection molded plastic or molded glass elements with diffractive surfaces are a reasonably priced and efficient choice, often used in hybrid refractive-diffractive lenses.
Finally, the sweat model provides a remarkably easy and intuitive way to grasp and understand the behavior of a diffractive surface from a conventional lens design point of view.
It's a clever trick proposed by W.C. Sweat. He showed that a ray tracing model consisting of a purely theoretical, extremely high refractive index, zero thickness lens could be used to accurately predict the effect of a diffractive surface at its design wavelength.
The higher the index you assign to this theoretical lens, the closer the results of the ray tracing approach to precisely matching the true diffraction effects.
With a refractive index of around 10,000 being a sensible value to use in practice. The model also includes a huge dispersion value related to the wavelength dependence of diffraction.
The Sweat model offers the immense simplicity and theoretical clarity of designing a diffractive lens by treating it as if it were a conventional refractive lens within standard ray tracing software.
Exactly. However, a main practical difficulty arises from the necessity of using such a large refractive index in the Sweat model. The ray tracing equations used in conventional optical design software can lose accuracy with very high values of refractive index, typically for values greater than 10 OIs or 10 era.
Nevertheless, for many practical applications, the necessary accuracy in the phase function of a keniform lens can be achieved with more manageable and convenient principles of refractive index, making it a powerful tool for modern optical engineers.
Yes, it's widely used, especially for designing hybrid lenses where the diffractive element cancels out much of the chromatic aberration of a refractive element, allowing for lighter and more compact designs like in some telephoto camera lenses.
We've truly taken a deep dive today, exploring the fundamental forces of light, the intricate mechanics of our own eyes,
the incredible mirrors and prisms that bend and shape light to our will, and the cutting-edge materials and designs that make it all possible.
From the tiniest photoelectrons that light can unleash to the vast electromagnetic spectrum that surrounds us, optical engineering profoundly touches every aspect of how we see and interact with our world.
It really does. Think about how utterly dependent we are on these precise principles and engineered marvels every single day.
What surprising new optical instruments or applications might be just around the corner, waiting to be designed and brought to life now that we understand this delicate dance of light and matter with such precision?
It's a fascinating question. Perhaps the future of vision itself, with enhanced human sight through augmented reality or even direct neural interfaces, or entirely new ways of perceiving the universe using parts of the spectrum we haven't fully tapped,
Yeah.
might be closer than we imagine.
All built on these very foundations we've explored today.
Absolutely.
Thank you for joining us on this deep dive. We hope this exploration has given you a fresh perspective and maybe a deeper appreciation for the engineered marvels all around us.
From the simplest reading glasses to the Hubble Space Telescope.
Until next time, keep exploring, keep learning, and keep asking those fascinating questions.